This is new, this voiceover. Okay, welcome everybody. So before I introduce Meena, I'll just remind you of how things work. So in the seminar, we try to encourage as much interaction as possible. So I've already discussed with Meena and she's more than happy to take questions during the talk. So please, raise your hand or write something to me in chat. And of course, Meena has also agreed to stay after the talk to answer questions, and we could also have an informal discussion session afterwards. So the talk will be recorded. So if you ask a question during the talk or in the official question session after, you will be recorded. And if there is anything weird that's happening that you want me to fix, then please let me know in the chat. So without further ado, it's my great pleasure to introduce Meena Mahajan from the Institute of Mathematical Sciences in Chennai. And she will tell us about refuting false QBFs with merge resolution. Please go ahead, Meena.
Thank you very much, Pavel. Thank you very much for the invitation to speak in this seminar. It's quite unusual for me to be talking at a logic and semantics venue, but I'm happy to talk about my work and get feedback from perhaps a slightly different perspective than what I normally see. Okay, so let me get started. I'm going to talk about refuting false QBFs. So this is a talk in the area of proof complexity. We're looking at quantified Boolean formulas which are false, and we're trying to prove in a formal system that they are false. And I'm going to describe one particular system, merge resolution, which I proposed with my co-authors. So this is joint work with Olaf Beerstoff, Joshua Blinkhorn, and Thomas Peitel at Jena in Germany, and Gaurav Sood, who is my PhD student at IMSc. And in this talk, I'm combining results from two papers. So in Stacks 2019, Olaf and Joshua and I had this paper where we first proposed this new system, and we showed some strengths of the system. And then more recently in FSCTCS 2020, we showed limitations of the system. Obviously, it would be too much to expect that any formal proof system has only strengths and no weaknesses, but we were not able to see them earlier, so it took some time. And so these results are spread out over almost 2 years, and I'm combining them in this. So to start with, let me first try and present what is the setting in which we are operating. What do we mean by these kind of formal proof systems, and what are we trying to do in them? So to start with, let's look at propositional satisfiability. So the question satisfiability, which we all know very well, it's is a question given a propositional formula, which I'm going to assume is in clause form, in conjunctive normal form, though this is not necessary as far as the computational complexity goes. So consider a formula given in conjunctive normal form. Here's an example. Clauses like this, and we just want to know whether there is some assignment, Boolean assignment, to the variables which satisfies all the clauses. So this is the quintessential NP-complete problem. It's a very hard problem, but the very hard is in theory, because if you ask practitioners who would like to reduce whatever real world problem they are trying, who would like to solve whatever real world problem they encounter, the first thing that many of them would do is to encode it as satisfiability and then give it to a SAT solver. And they say, if you can encode it succinctly as SAT, then you're through, because SAT solvers are phenomenally good at solving real world problems. So in fact, with the tremendous success of SAT solvers, so there has been fairly ambitious ongoing programs around the world to design good solvers for problems which are harder than SAT. I mean, now that many people do feel that SAT, at least the instances of SAT that seem to be arising from practical applications are easy to solve, let's try and solve harder instances. So in this talk, I'm going to be looking at QBF, quantified Boolean formulas. So what are these? Well, QBF, it obviously subsumes SAT. So earlier, the instance of SAT that I gave, I just had a bunch of clauses, whereas now I'm sticking in these existential quantifiers before that. So this is a sentence, and I want to know whether this sentence is true or not. So the QBF subsumes SAT completely, but it is more expressive than SAT. Well, not more expensive, it is more succinctly expensive than SAT. It can say things, it says in QBF you express the same things that satisfiability can express, but probably with much shorter formulas. So an example of a QBF formula which is different from SAT would be something like this. There exists a U for all, E for all U, there exists C, there exists D, and then again there's a bunch of clauses which involve these variables. And now the question is to decide whether this sentence is true. So it's no longer a question of is it satisfiable, because this entire sentence takes just one value, true or false. And this question, from the computational perspective, we understand very well. This is p-space complete. So in that sense, we also understand to what extent it is harder than SAT. SAT is NP complete and QBF is p-space complete. So we are going to consider QBFs which look like this. So they are totally quantified. There are no free variables. The formulas are in Prinex form. So all the quantifiers appear in the beginning, and then we have all the clauses. Well, it's also the inner formula is in conjunctive normal form. So it's clauses, disjunctions of literals. So again, this is a format in which one can write a QBFs, which we know does not really matter from the computational perspective. But in terms of formulating a proof system which can operate on the given formula and manipulate it to, in a formal sense, refute this, it's good to fix a particular syntax. And the systems that we are looking at are going to be working with this syntax. Okay, so the question which we are looking at is given a formula which looks like this, which is presented in this form. The formula is known to be false. We want to write down a proof that it is false, and the proof we are hoping is not going to be too long compared to the size of the formula. So what kind of proofs are we going to accept? So the reason we are doing this is because, like I said, generalizing from the success story of SAT solvers, there are now QBF solvers which solve exactly this task. Given a QBF, they try to decide whether it's true or false and give a proof in either case. Now, these solvers are they're obviously heuristics based because they're tackling a p-space complete problem. So underlying these heuristics are formal proof systems. When you run the solver on a satisfiability instance or a QBF instance, and in particular, if you run it on a false QBF, the trace of the algorithm, which finally stops and says, hey, this formula is unsatisfiable, that trace is providing a proof of unsatisfiability in the case of SAT, or it's providing a proof of the fact that the QBF, given QBF is false. So now underlying this solver heuristic is a formal reasoning method, which is essentially, that is what I'm talking about as a proof system. There is some kind of formal reasoning which is underlying this. And in this system, if we can show that there is no short proof of falsity, then it means that this, for a particular QBF, then it means that this QBF, when fed to the QBF solver based on this proof system, will not have a short run, because the run itself is the proof of falsity. So that's where proof complexity comes in. That's one of the places where proof complexity comes in. Proof lower bounds for proofs of falsity of QBFs. And one use of such lower bounds is that it's going to tell us where the QBF solvers are likely to flounder on such QBFs, and where we would want to perhaps try and improve these solvers. So one thing which will repeatedly come up in the context of QBFs, and in the way in which we also abstract from the heuristics into a formal proof system, is the fact that deciding the truth or falseness of a QBF is related to this very well-known two-player evaluation game. So you have the QBF, you have two players, red and blue. So red owns the existential variables, let's say, blue owns the universal variables. They step through the quantifier prefix and they assign Boolean values to the variables as they go along. So by the time they reach the end of the prefix, they have constructed an assignment to all the variables, because it's in Prinex form. And then we can just plug in this assignment into the inner formula F and check whether the formula is true, whether all clauses are satisfied. If all clauses are satisfied, then the existential player has won the game. Otherwise, the universal player has won the game. So a very simple example. There exists X for all U. Now this inner formula, you can see it actually is saying that X is equal to U. So if red plays X equals 1 and then blue responds with U equals 1, then red wins. Both the clauses are satisfied. But if red plays X is 1 and blue says U equals 0, then one clause is falsified. If red says X is 0 and blue says U is 1, then another clause is falsified. So in both these cases, the blue player wins. And again, like I said, in this example, the universal player can always win simply by setting U is not equal to X, or U is the negation of X. So that's the Herbrand function, which witnesses that this formula is false. So now, so this is something that is well known, that a QBF is false if and only if the universal player in this particular game has a winning strategy, a strategy to decide what value to assign to the variables as and when that this player's turn comes up, such that no matter how the other player plays, some clause will always be falsified. Now, this game is very often used to even argue that various proof systems are sound. And in our system, we are going to really turn this around on its head and use these games in a very different way, which is why I wanted to say this right in the beginning. Okay, so now let's move towards trying to formalize a proof system. So we are reaching QBF by generalizing from SAT. So first, let's examine what's done for SAT. If you look at satisfiability, one of the most well-studied systems is resolution. So you have a bunch of clauses. You're trying to decide whether these clauses are simultaneously satisfiable. If you already have two clauses of the form C or X and D or negation of X, then you can infer C or D. This is an inference rule. All it says is that any assignment which satisfies both the premises will satisfy the consequent. For propositional CNF formulas, if you add clauses derived via resolution, then satisfiability is preserved. And the goal in a resolution proof would be to derive the empty clause. The empty clause we know is definitely not satisfiable. So if we succeed in deriving the empty clause, then we know that the original formula is not satisfiable. And the way we have derived the empty clause is a certificate, a proof of unsatisfiability. Okay, so for propositional CNF formulas, the resolution rule is sound. Whenever you can derive the empty clause, indeed the formula is unsatisfiable. It's also complete. Whenever the formula is unsatisfiable, indeed it is possible to derive the empty clause starting from the clauses of F. Okay, so therefore resolution by itself forms a proof system. So the resolution is providing the syntax in which we will write down a proof of falseness of this formula. It's one of the most well-studied propositional proof systems. It underlies most of the practical SAT solvers which are around. All those SAT solvers which I said have seen such stupendous success. Of course, they don't do just resolution, they do other things also, but resolution is the core underlying idea. Okay, so now we want to take this idea of the way resolution works on clauses and try to see how to adapt it to demonstrate the falseness of QBFs. So what happens if we start using resolution on clauses when the clauses come from a quantified Boolean formula? Well, it continues to be sound. In the case of resolution, we said, in the case of in the propositional case, we said resolution preserves models. Even if the formula is a QBF, it preserves. So models for a QBF would be Skolem functions, and resolution preserves those functions. But if you already have a bunch of clauses in the inner formula, you can add more clauses to it through resolution, and the same Skolem function will work. Okay, but resolution is not complete. And that should be fairly easy to see. For instance, the same example that we saw earlier, there exists X for all U, X is not equal to U. It's a blatantly false formula. But if you were to use resolution on this, what can you do? If you resolve on X, then you get U or not U. You resolve on U, you get X or not X. In either case, you derive something which is true. So there is no further path towards deriving the empty clause. And this happens because we are treating X and U as the same. They are not the same. U is universal. It should be, we should be allowed to handle it differently, do things with U which perhaps we will not be allowed to do with X. So we need to augment this resolution rule with something else. And there are, in the literature over the last 20-25 years, there have been, broadly speaking, two ways in which resolution has been extended to handle QBFs. One is based on expansion and one is based on reduction. So I'm going to just show one slide on each of these to kind of describe what's going on. What happens in an expansion-based system? So the idea in an expansion-based system is that if I have a QBF in which the outermost quantifier is a universal form quantifier for all U and then something inside, well, this is true if and only if the inner formula expanded on 0 is true and the inner formula expanded on 1 is true. And in this, the inner formula may itself be a QBF. I'm not saying that U is the last quantifier in this, but this is just the semantics of what the universal quantifier means. And now this formula, which I've written on the second line, is no longer in Prinex form. And for us to be able to recursively construct proofs, we want to be able to deal with the same format of a formula at every stage. So we want to Prinex this. So when we Prinex this, the inner formulas are talking about these variables X, but the X variables in this copy are different from the X variables in the second copy. So we will need to kind of label them accordingly. So then we get this larger formula. And again, it's completely straightforward that this formula on the third line is true if and only if the formula on the first line is true. Now, so all that we are doing is we're saying eliminate the universal variables. And this is obviously going to be very expensive. You start off with a formula, by the time you eliminate all the universal variables, your formula has blown up. So the whole idea is to expand the initial formula judiciously. Maybe you do not need to really expand all the clauses fully across all possible settings of the universal variables. And indeed, many heuristics which are used in QBF solvers show that some expansions are not even needed. So amongst all possible expansions of the clauses, maybe there is a smaller subset which is enough. You take that smaller subset and then you use standard resolution. And the standard resolution that we're using, of course, this resolution will have to make sure that it treats these variables as two different variables. X annotated with u equals 0 is different from X annotated with u equals 1. So these are the expansion-based systems, and these were proposed, I think these are the years when the journal papers arrived, but they were proposed even earlier by Miklos Janota and João Marques Silva. That was in 2015. They proposed the system for all expansion, universal expansion and resolution. And then Olaf Beiersdorf, Leroy Chu, and Miklos Janota, they generalized this a little bit more to what is called instantiation and resolution. So these are two resolution-based proof systems around in the literature for QBF. They are sound and complete. And at least the first of them, for universal expansion plus resolution, does underlie a QBF proof solver that is used in, that has been implemented successfully. Okay, so this is the idea in an expansion-based system. What about the reduction-based system? So the universal reduction rule is another way in which you can add to resolution to get a proof system for QBFs. Suppose I have a formula which looks like this: some quantifier prefix with the X variables, then a for all U, and then a quantifier prefix, some more quantifiers on the Y variables, and then a bunch of clauses. So suppose this is a formula which is true. And in this formula, there is a clause of the form C or LU. LU is a literal based on U, so it's either U or negation of U. And all the variables in C come from X. So in some sense, when you look at the order and the quantifier prefix, this universal variable U is the rightmost according to that order. Now if I start with a QBF which is true, and there is a clause in it in which LU is the rightmost, in which the universal variable is rightmost, then I can add to the bunch of clauses the clause I get by removing this LU. So removing LU is equivalent to setting U in such a way that the literal LU becomes false. So I get a new clause and I add that to my bunch of clauses, and the formula still remains true for the same reason that the Skolem function, which earlier witnessed that it was true, will witness that this is true also. That Skolem function could not possibly have banked on, C or LU is going to be satisfied by LU, because LU is going to be set by the adversary. So it would have had to satisfy the C part already. So this is what the reduction rule says. If you have already derived a clause in which a universal variable is rightmost, then you can drop the rightmost, that universal variable in whatever polarity it appears. Models will be preserved. So now you use resolution, you use universal reduction repeatedly. And suppose, as in the case of resolution, you are able to finally derive the empty clause. Well, you have preserved models. The empty clause has no models. So therefore, the original formula was false. Okay? So these are the universal reduction. This is the universal reduction rule. And now the proof system is a system which has two inference rules: resolution and universal reduction. And this is used in the proof system QU resolution, quantified universal resolution, which is basically resolution plus universal reduction. And this was a system which was proven to be sound and complete by Van Gelder in 2012. But actually the precursor to this was QRES, one of the first, not one of the first QBF proof system, which was, I think, discussed sometime in 1995. And that is a special case where resolution is allowed only on the existential pivots. So when you're saying C or X, D or not X, infer C or D, X must be existential. And even that is enough for completeness. So QRES is a fragment of QURES, which was, like I said, proposed 25 years ago. But a formal proof that this system is sound and complete came only in 2012. And that formal proof, in fact, showed that even QURES is sound and complete. Okay, so like I said, there were two ways in the literature, standard ways of extending resolution: expansion or reduction. There is a third way which goes a little bit beyond reduction, and that is merging complementary literals. Okay? And this way says that, okay, you have this formula, there exists X for all U, our old formula saying that X is not equal to U. Earlier we said that resolving on X is useless because you get a tautology U or not U. But now I would like to say that this is not useless. I'm going to merge you and not you into a new symbol, U star. And U star is not it does not mean the tautology you or not you. What it means is that, yes, I do have a strategy for you. Because I have obtained this U star by resolving on X, the strategy which tells me how to assign U is going to depend on that pivot X. So U star is just a placeholder for such a strategy. And now maybe in resolution, I extend resolution by allowing such placeholders, but without formally specifying what is the strategy. Just saying that, yes, I know such a strategy exists. And then maybe we can continue and go ahead with this. So this is a much more complicated proof system. The analysis that such proof systems are sound is much more tedious. So this is using a rule of this type. The system long distance queue resolution was proposed by Balabanov and Jiang. It was actually used in a rule like a heuristic rule like this was used in QBF solvers more than 10 years before that, in 2001. But what was underlying that proof system? The proof system has had a heuristic. How do you abstract that into a proof system? That was done a little later. Then it was proved to be sound and complete. And then there were various extensions of that, LQU plus IRM and so on, which were also proved to be sound and complete, and increasingly more and more powerful. So they all use the idea that apart from resolution and either universal reduction or expansion, apart from these two things, they also use merging. Okay, so this was what was around before we started our work. And already there seems to be a zoo of proof systems which can deal with QBFs based on resolution alone. I'm not even talking about proof systems which are not based on resolution. And now we are proposing yet another system based on resolution. So what is new in the proof system that we are looking at? Well, more than what is new, first, like what are the main features of this proof system? So in this proof system, the clauses that are carried along at every line are based on existential literals alone, not based on universal literals. So in that sense, this looks a little bit like expansion-based systems. In the expansion-based systems, we effectively threw away the universal variables. They appeared by making copies of the existential variables, but when we actually were doing resolution, there were only existential variables in our system. So here also we have only existential variables when we do resolution, carry the universal variables in a slightly different way. So what is that different way? We maintain partial strategies for universal players alongside each clause. Okay? So this is a bit like long distance resolution, and maybe this will become clearer when I give an example. To apply resolution, so we have some clauses which are talking only about existential variables, and we want to apply resolution on them. The resolution rule is the same old rule, but we are going to have some side conditions that even though if ignore everything else, maybe it's possible to resolve these two clauses. But I'm going to look at the partial strategies, the antecedents, and then in some cases I will say that even though the clauses are of the form C or X, D or not X, I will not permit the resolution to derive C or D because the partial strategies satisfy some blocking condition. So there are conditions on the strategies which will tell me when the resolution is to be permitted and when it is to be forbidden. Okay. These conditions that we have on the partial strategies, they must be efficiently checkable, because the whole idea of having a proof system is that line by line, if you are checking, is this a proof that the formula is false or whatever, that checking should be possible efficiently in polynomial, at least in time polynomial in the size of the proof. So if I want these conditions to be efficiently checkable, it means that the way I'm representing those partial strategies, the choice of representing these strategies is restricted by this fact. So certain kinds of checks can be done efficiently, certain kinds of checks cannot be done efficiently. So that's going to play a role. Okay, so what does merges actually achieve? So it builds the winning strategy of the universal player. So remember, the winning strategy of the universal player is like these Herbrand functions that we are building up piece by piece. So we are building them into the proof itself. So we start off at every clause, there is a function which may not be a full Herbrand function, but it works for that one clause alone, perhaps. It's like a partial strategy or a trivial strategy. And as we perform more and more resolution, our strategies become more and more complex. By the time we derive the empty clause, we have a full Herbrand function. This is built into the proof. And this is the major point of departure from earlier proof systems. The earlier proof systems, they did not have the winning strategies explicitly represented. In fact, one of the ways of proving that those proof systems were sound was to say, okay, give me a proof in that proof system. I will extract from it a Herbrand function, or I will extract from it a winning strategy. And the very fact that I can extract such a strategy means that the formula was false to begin with. Hence, the system is sound. So extraction of strategies was used earlier to establish soundness, whereas we are building the strategy description into the proof itself. So extraction of strategies is trivial in our system because it's already there. It's explicitly represented. So this is going to make some things easier and it's going to make some other things harder. Our choice for how to represent the partial strategy is going to be binary decision diagrams. And the binary decision diagrams are underlying each such decision diagram. There's a graph. The graph structure is going to mimic the derivation structure of the clauses. So a very brief reminder in case this notation binary decision diagrams is unfamiliar. It's basically a directed acyclic graph like this. There's a start node. Nodes are labeled by variables. So you query a variable. Here I start off, I query x1. If x1 is 0, I go in this direction. If x1 is 1, I go in. So each node has two out edges, one labeled 0, one labeled 1. So you query the variable. Based on the value you get, you go to a successive node. And finally, eventually you will reach a sink. There are only two sinks. One is labeled 0, one is labeled 1. The sink that you reach is the value of the function. So this decision diagram is trying to compute some function of the variables x1, x2, x3. And given an assignment, it tells you how to walk through this graph to reach a sink. Whichever sink you reach, that tells you the value of the function. So that's what a binary decision diagram is. It's at each node you're making a decision based on your assignment, and finally you have the function value. So our winning strategies are Herbrand functions, and we are going to represent these functions by binary decision diagrams. Okay. So that's one thing that we do in our proof system. So what is the syntax of a proof line? So thinking back to what happened in the case of satisfiability, every line in a proof was just a clause. And to start with, we had all the clauses from the initial formula. We pull down one line at a time, and then maybe from two preceding lines, which we have already pulled down, we derive a third line and so on. But every line is a clause. Now in this merged list system, every line has multiple components. It has a clause C, which is a clause which has only existential variables. And for every universal variable, it has a binary decision diagram, which computes some function for that variable. So for different variables, different universal variables, it has different. So if my QBF has 5 universal variables, then each line looks like one clause on the existential variable and 5 binary decision diagrams. Okay. So each decision diagram is computing some function H. What we are going to do is we are going to view the resolution proof part, the part which is looking just at X, as we're going to view that resolution proof itself as a decision diagram implicitly. And it's a decision diagram for a different function. It's a decision diagram for the function. If I give you an assignment to all the existential variables, well, this formula is false. So therefore, the universal player should have a way of responding such that some clause from the initial formula is falsified. Can I find that clause? So we'll start with the resolution proof. The final clause is falsified by any assignment, but that final clause is resolving on X. One direction has X equals, comes from a clause with X, another direction comes from a clause with X bar. So if my assignment has X equals 0, I should not be going in the direction of X bar because that side the clause may be satisfied. I'll go in the direction where the literal is falsified. And in this way, I can just walk up the resolution tree until I reach an axiom. That's what happens in satisfiability. But now we are in QBF. So in QBF, we'll again start at the end of the proof, the goal clause, which was the empty clause, walk up based on our existential assignment. And suppose we are able to reach a line like this, C and a bunch of formulas, a bunch of BDDs. What the semantics that we will be able to establish is that if this is the line we reach, then the assignment alpha that we use to reach this line and the values obtained by all these functions when the input is alpha, to that assignment together falsifies at least one of the clauses that was used to derive C. So this clause C didn't come out of anywhere. It was derived using some clause. So some of the initial clauses must be falsified. And the proof is guiding our search towards that clause. Okay. So if this is the intention, then how do we set up the system? So maybe before I set up the system, I should just give a simple example because that may motivate it. It's fairly notation heavy, right? Okay, so here's a formula. There exists X for all U, there exists T, and then there are these clauses. Okay, so the last clause tells us that T must be true, that T must be false. And if T must be false, then these two clauses simplify to X or U, X bar or U bar. So X should be the opposite of U. But then that's how the winning player is going to kill the existential player by setting U to be equal to X. Okay, so how are we going to refute this in merge this? We're going to say, okay, let's look at this first clause, X or U or T. The existential part of it is X or T, if you throw out the U. But now if this is the clause that is going to be falsified in my final, in the final run, then it must be the case that U should take the value 0. So the function which I'm representing on the side, there is only one universal variable. So there is only one BDD on the side, and that BDD is the constant BDD which takes the value 0. So for this clause X or U or T, my proof actually has the existential clause X or T and the BDD with constant 0. For the clause X bar or U bar or T, my proof is going to use the existential clause X bar or T and the constant BDD where U is 1, because that is what falsifies this literal. And for the clause T bar, we can use the clause T bar. What should the BDD be? Well, the BDD, you don't even care what is the value of U. So we're going to use this special symbol star to say, I don't care what is the value of U. Now we perform resolution on the existential part. X or T, X bar or T, I can resolve. And I get T. What should be the strategy for U? So if I give you an assignment to X and T, and I say, what should the value of U be? Well, on this side, we're saying U should be 0. On this side, we're saying U should be 1. But when would I go on to this side? When X is 0. So really, I want to say that when X is 0, copy the strategy from the left. When X is 1, copy the strategy from the right. So these two strategies, which were initially the trivial BDDs, now get spliced together, merged together into a more complex strategy. Okay. Now these two clauses, when I resolve T and T bar, I have a complex strategy here, but I have a don't care strategy here. So the don't care strategy you can discard and just copy this. And this is, in fact, I have derived the empty clause, and I have a winning strategy for U. This winning strategy says if X is 0, U should be 0. If X is 1, U should be 1. So this is what merge rest tries to do. Work with the existential part of the clause and build up a strategy for the universal variable. This was a very simple example. It had just one universal variable. We could have multiple universal variables. But before we go to that, maybe I should just look at a non-refutation. So here is a QBF which is true. For all U, there is a T which is equal to U. That's true. Okay, so these two clauses encode that T is equal to U. But now suppose I do the same thing that I did in the previous slide. This U bar or T, the existential part is going to be T, and the constant BDD will say set U equals 1. And U or T bar, the existential part is the clause T bar, and the BDD will be set U equals 0. And then I try to resolve T or T bar. I get the empty clause. And I get this, I piece together these strategies, and I get a decision diagram which looks like this. This is obviously wrong. So what is wrong here is that we tried to piece together strategies for U from the two clauses. But the pivot at this stage, the resolution pivot at this stage, was a variable on which U does not even depend. If you look at the prefix here, T comes after U. So U is not allowed to query T. Any the Herbrand function U, T is not even one of its variables. So in that case, so what I want to say is that if I want to resolve on T, I have two clauses, one has T and one has T bar, and there are partial strategies on both sides. I cannot merge those partial strategies. This resolution will be allowed if the partial strategies on both sides are the same. The resolution will also be allowed if one side does not have a strategy at all. It is just trivial. But if the strategies are different, this resolution is blocked. I simply cannot. So this is the side condition that I referred to earlier. That if we ignore the strategy part, then it looks like resolution is possible. But resolution is not allowed under these conditions. So this is not a valid refutation for this reason. And this is what we need to encode into the, put into the definition of the system. So now with this, let me describe what are the rules of merge rest. From how do we start? If the original QBF has a clause C, then in my proof system, I can use the clause D, which is the existential part of C, and attach to it these binary decision diagrams, which are all constants. For a variable U, which appears in C, if U appears in C, then the constant 0, because U should be set to 0 to falsify this clause. If negation of U appears in C, then U should be set to 1 to falsify this clause. If U does not even appear in this clause, then I don't care what is the value of U. For each universal variable U, I construct a BDD which has just one node with a value 0, 1, or star. And now what this means is we're saying take any assignment to the existential variables. If it falsifies D, which is the existential part of the clause C, if it falsifies D, then that assignment along with these partial strategies is going to falsify C. Okay. So this is what we can do right in the beginning. What do we do at a resolution step? So at a resolution step, I already derived a clause C1 or X, and it comes with a zoo of BDDs for each universal variable. I have derived C2 or X bar with a different zoo of functions, and then I want to resolve them on X. So I want to derive C1 or C2. And in the process of deriving C1 or C2, the binary decision diagrams will change from M1U for each U. For each universal U, M1U and M2U should be combined together in some way to produce MU. How do we combine them? Well, if one of them is don't care, then I can just copy the other. If M1 is star, then copy M2. If M2 is star, copy M1. If neither of them is star, but they are isomorphic, or essentially they're computing the same function, then it doesn't matter. You can copy M1. Okay. So this is one point where we will need to be able to check that they're isomorphic. So that is one reason why we chose this representation binary decision diagrams, where we can check this efficiently. Now, one more condition. Maybe U comes after X. So X was the pivot in this resolution. U comes after X. Sorry, was there a question? No. Okay.
No, I think it was just some noise from a mic.
Okay.
Please go ahead.
Yeah. So here is another possibility, that U is a variable, universal variable, which comes after X. M1 and M2 are not the same. They are different. But I am allowed to combine them. I'm allowed, because U does depend on X. So I can combine them and I can say, look, if X is 0, then choose the strategy coming from M1, and otherwise choose a strategy coming from M2. But if I do this, my strategy may become big. So therefore, I also attach this condition that M1 and M2 are consistent. So whenever they use the same nodes from the proof, they use them in the same way. So I put together this M1, M2 by reusing the common nodes. So I actually get not a tree, but a directed graph. Okay. And this is the only case in which, I should have. So these are the only cases in which I can do resolution. So if U is less than X and M1, M2 are not isomorphic, then resolution is not even permitted. And that was the fake refutation that we saw earlier, which was leading to problematic refutation. So those refutations are blocked. You cannot perform those resolutions at all. So this is the syntax of the proof system. Okay? And yes, it needs some work to prove that this is sound, but not that much, because the way these strategies are built up, like I said, the meaning of each line is clearly encoded into this. Completeness comes from just looking at the entire assignment tree and then figuring out how to build up these functions. So both soundness and completeness, although it's notationally heavy, conceptually it is not very difficult. The really interesting thing is, having done all this, does it bias anything over the other systems? We had these expansion-based systems, we had the reduction-based systems. Now here we are doing something different. And what is the use of doing this? Okay. So the first thing I would like to say is that, yes, it does bias something more. Here are these formulas, which are known as the equality formulas. Okay. So it's a family of QBFs. The nth QBF looks like this. There exists a bunch of, there exists x1 to xn for all u1 to un, there exists t1 to tn, and here are some clauses. Let's just stare at what these clauses are. So if this formula were to be true, if the existential player had a winning strategy, then that winning strategy must set at least one t to false, because of this long clause here. And the moment that t is set to false, it means that in that group, the xi or ui and xi bar or ui bar, both these clauses must be satisfied irrespective of ti. But these clauses together are saying that xi is not equal to ui. And now the universal player is going to kill the existential player's chance of doing this by setting every ui to be equal to xi, which is why this is called the equality formulas. If each ui is equal to xi, then the only way of satisfying all the n clauses is to set all the t's to true, and then you have lost the last clause. So this is a false QBF. Okay? So this is a false QBF. There is a unique winning strategy. The unique Herbrand function is that each ui must be equal to xi. But this formula is extremely hard to refute. In the expansion-based systems, it requires exponential size. In the reduction-based systems, it requires exponential size. And the reason it requires exponential size in both the systems is somewhat different. But yes, so these formulas are known to be very hard. And it turns out that these formulas are very, very easy to refute in merge res. In fact, the merge res derivation graph in which we finally derive the empty clause, not only is it small, almost linear size, it is even a tree. You don't even need the properties of a DAG. It's tree-like. It's even regular. By regular, I mean that you do not resolve on the same variable more than once along a path. It's a very simple derivation. And let me very briefly sketch what the derivation looks like. So you start with the just a quick reminder. So you have this PI and NI clauses which look like this, and that's what I've written up here. So if I take the clause XI or UI or TI, then in our system, it means that you will use the clause XI or TI, the existential part alone. And you will say that, look, the ith variable UI, my partial strategy says set it to 0. But for the remaining variables, I have no partial strategy. I don't care because they don't figure in this clause. So my sequence of n binary decision diagrams, well, n-1 of them don't care. And just one of them has a value 0. On the other hand, in the negative clause, XI bar or TI, again, I have n-1 don't care strategies, and I have one strategy, which is a 1. The UI appears negatively here, so I must set UI to 1. What happens when I resolve these? Well, this resolution is not blocked. It's permitted to resolve these on XI because UI does depend on XI, and then I will construct, what will happen is that the BDD for UI looks like this. UI equals XI. The other BDDs, all the other variable BDDs remain trivial. So I can derive all the unit clauses TI, each with an associated partial strategy. And now I just start with my long clause, which had no strategy to begin with. And one by one, I cut out the T's, cut out TN. So the one don't care becomes the strategy for UN. So I've abbreviated this little binary decision diagram here by just xn because it's computing the function UN equals xn. So this becomes xn. Then I cut out the next variable. This becomes xn minus 1. Okay. At each stage when I'm doing this resolution, you have these n possible BDDs, and coordinate wise, at each coordinate, one of them is trivial and one of them is not trivial. So there is no blocking. All the resolutions are permitted, and you can go on to derive the empty clause. And at that point, your set of strategies has exactly the unique winning strategy. U1 must be set to X1, U2 must be set to X2, and so on. So this is a very small and simple proof that equalities formulas are false. This can in fact be generalized a little more to a formula which is a squared equality, where those t variables come in a square. And I think since I don't have that much time, I'm not going to look at, I'm not going to give this in detail, but I had put up a proof here just to show that it was in the equality example, all the resolutions had a don't care and a non-trivial strategy. But it could even be that some resolution steps are allowed because the strategies on both sides actually match. So it's not that one of them is don't care and the other is not don't care. Neither of them is don't care, and they are in a variable which is appearing before the pivot, but they are the same. So we have this isomorphism check, and so it goes through. So I'll just skip the details of this. Here's another example which I would like to spend a minute or two. The Q parity formula. There exists an x1 to xn such that for every z, there's just one universal variable z. There exists a t1 to tn. And now my bunch of clauses, I have not written it in clause form, but you can see that each one of these, it's looking at a few variables, so you can convert it to clausal form. X1, there's a typo here. X1 is exactly equal to t1. Each ti is equivalent to the parity of ti minus 1 and xi. So if all these clauses are satisfied, then you can see that tn will be the parity of x1 to xn. Okay. But then there are these last two clauses which say that tn is not equal to z. So if we want to satisfy all these clauses, once the x values are chosen, then to satisfy all these clauses, it must be the case that z is not equal to the parity of xi. So the universal player who is trying to not satisfy all the clauses will set z to be equal to the parity. And then no matter what t is chosen, either you will lose one of the earlier clauses and which dictates the value of t, or you will lose the last clause. Okay, so this is a false QBF. It turns out this formula is also very hard to prove in the reduction-based systems. It is not hard in the expansion systems. In the expansion-based systems, it has linear-sized proofs. But in the reduction-based systems, QRes, QUres, it's exponentially hard. And the hardness comes from the fact that the strategies extracted are small depth circuits, and we know that parity is a function which is hard to compute in small depth circuits. It's something which is not expressible in first order logic. So the hardness comes from there. In mergers, this formula is easy. It's easy even if we insist that the proof is regular. So these examples show that mergers is able to do things that defeat the other systems in some way or the other. Okay. How do you go around proving lower bounds? Okay, I can see that I'm going to skip some of these but I think at this point, let me mention the results themselves. So the parity function has circuits of small size, and but if you insist on a decision tree for parity, so what is a decision tree? A decision tree is a binary decision diagram in which the underlying graph is a tree. So it does not, as opposed to a directed acyclic graph, you're not allowed to revisit the same node along two different paths. It's a tree. It's relatively very easy to show that decision trees for parity must have size 2 raised to n. You have to go along different, all the 2 raised to n assignments have to be explored separately. So now if I insist on a merge res refutation, which is tree-like, which does not reuse clauses that have been derived, the partial strategies that merge res builds are always isomorphic to the derivation graphs. So if the derivation graph is a tree, then the partial strategy will also have to be a tree. The decision tree has to be exponential in size, which means that the proof will also have to be exponential in size. So even though parity, this Q parity formula is easy for mergers, it is not easy for a tree-like version of mergers. Similarly, there is another formula here, the completion principle, which is not easy for a tree-like version of mergers. And the reason why it is, with the completion principle, the important thing is that it has multiple winning strategies. Unlike parity, which had a unique winning strategy, here there are multiple winning strategies, but we are able to show that it doesn't matter which winning strategy you use. Each one of them is hard for decision trees. So you have a choice of which function to pick up for the universal player, but they are all hard if you want to represent them as trees, and therefore there is not going to be any short tree-like mergers proof. So decision trees is a computational model in which we know how to prove many lower bounds, and we can use those lower bounds to design QBFs where the functions which are hard in decision trees are the unique Herbrand functions, or all the Herbrand functions are coming from that set. Then that formula will be hard to refute in tree-like merges. Similarly, if you look at regular merges where no pivot is used more than once along a path, then the strategies that are constructed in regular merges proofs, they are again BDDs. They are no longer trees because this is not a tree-like refutation, but they are read once BDDs. The regularity condition here corresponds to read once. On any one path, if you follow in the BDD, you are not reading the same variable more than once. Read once BDDs is again a computational model in which we do have explicit lower bounds. We do know explicit functions which have small circuits, but if you insist on read once BDDs, then you require exponential size. And you can design QBFs where these functions are the Herbrand functions. Then those QBFs will be hard to refute in regular merges. The parity function itself is not hard for read once BDDs, but we can tweak the parity formula slightly. There is a version of it called LQ parity. In this tweaked version, again, the only winning strategy is parity. But this tweaked version we can show is hard for regular merges. So now this hardness for regular merges is not coming from computational hardness. Okay, so now this is something different which is happening. We are constructing a formula in which the winning strategy, there is only one winning strategy. That strategy is computable by read once BDDs, absolutely no doubt about it, by small read once BDDs, but still the formula is hard to refute. So we have a different source of hardness. It's not just computational hardness. So this was still for special cases of merges, tree-like or regular. For general merges, we do not yet have a technique which will give, what is a method which can be used to give lower bounds, but we do have a combinatorial argument which is fairly involved, and I would really like to at some point see a simplification of this. So it's a combinatorial argument with which we are able to show that a particular family of formulas, these formulas have this very strange name, KBKF. KBKF is actually the acronym coming from the names of the authors. So the first QBF proof system that I mentioned from 95 was proposed by Kleine-Buning, Karpinski, and Flogel, and they described these formulas. So this is the Kleine-Buning, Karpinski, Flögel, the KBKF formulas. And then subsequently it was modified slightly, the KBKF formula, to make it hard for a long distance system. So these are the formulas KBKF, LQ, which we show are hard for merges. They are easy to refute in QURIS. In the reduction system, QU, they are easy. And using, like I said, using these elaborate combinatorial arguments, we are able to show that they are hard. So here, finally, let me put up a picture of what's happening. So this is the new system that we defined. But before that, the systems which were around, these were the reduction-based systems, QRES and QURES. And there is, in fact, one more system which I've drawn here, but it's not a resolution-based system. It's cutting planes and a universal reduction system. Okay, it sits over here. But these two are the reduction-based systems that I talked about. These two are the expansion-based systems that I briefly mentioned: expansion plus universal expansion plus resolution and IR. And here is the long distance system. And there are various relations already known amongst these systems. QU is strictly more powerful than Q, IR is strictly more powerful. These things are incomparable, and so on. Now we have this new system, which we have brought up here. From the results I mentioned about equality, about KBKF, we know that MRES is incomparable with QURES. There are formulas which are easy in MRES but hard in QURES, and there are formulas which are easy in QURES but hard in MRES. The tree-like fragment and the regular fragment of merges are incomparable with all of these. Whereas for merges, I still don't know whether it's incomparable with the expansion systems. I know that it can do something that the expansion systems can't do, but I don't know the other direction. So looking at these incomparability results, it seems like something non-trivial is going on with merges, because there are strengths and weaknesses which are coming from different sources. So this should be the right slide with which to end, but maybe I'll show this summary slide and one more slide which has a few questions and directions. So what I did try to describe today was, I started with the existing paradigms for obtaining QBF proof systems based on resolution. They were expansion and reduction, universal reduction, and then described a new approach, which was merging partial strategies. It builds strategies into proofs using compact representations, and each line has a clear semantic meaning. And with this meaning, we are able to enable inference steps which are sound, but some other systems, existing systems, did not realize that they were sound and syntactically just blocked them. And this is what gives it its strength. The equality formulas are easy here because we are able to detect that the inference step that we are trying to use is sound. So this is what gives it exponentially more power over QURES and IR. On the other hand, it is exponentially weaker than QURES, and it's not very clear where that weakness is coming from. Okay, like I said, it's there was an ad hoc combinatorial argument to show that this formula is hard, but there has to be a better explanation for what it is that merges is unable to do. What I have not discussed here at all is a small adaptation of merges augmented by one more rule, a weakening rule. This yields a sound and complete system for dependency QBFs, and dependency QBFs is even more succinctly expressive. It is NEXP complete, but that's something that does not really fit into this talk at all. So this is a summary of what I tried to describe today, and here are the questions which I think are interesting. The first question is really a representation question. The merger system, it gets its unique features, so to say, and its strength, perhaps also its weakness, but certainly its strength and its USP from the fact that it is representing partial strategies inside the proof. The choice of the representation matters, because if you use a very elaborate strategy like circuits, you won't be able to check whether the strategies are isomorphic and therefore whether the inference step is blocked or not blocked. So are there other representations that can be used for which these isomorphism checks go through, where more advantages can be obtained? No? So we have these two conflicting requirements. The representation should be succinct, but equivalence checking should be easy. So like I said, this is a computational question, and then it will probably tell us something about the complexity of refuting the QBFs. The second question is, like I said, the combinatorial argument I'm not so happy about. I would like to see what is the underlying lower bound technique, which then I can try and apply to many other formulas rather than an ad hoc argument. And the third question here is, then what sits on top of merges? So it cannot be that merges is is all powerful. We have already seen some limitations of it. There must be some systems already around in the literature which are powerful enough to simulate this, but we have not been able to establish exactly what they are. So these are some of the questions that I continue to think about, and I think that they are interesting. Yeah. So I think with this, I'll stop. I'll wrap up. Thank you very much for your attention.
Thank you, Meena. That was very clear and very interesting. Are there any questions? So either, maybe I'll turn on the chat so that's, and if you have a question, please go ahead. Okay, we don't have anyone brave enough, so maybe I'll ask one. So when so in your system, you're building out these proofs, and it's basically if I understood correctly, it's a combination of resolution and building up these BDDs, right? That's as part of the proof. So in a complete proof, you would, I mean, and you build up one of these BDDs for every single universally quantified variable. So you have these various BDDs inside of this proof tree. Yes. Now, I guess the obvious thing, I mean, maybe it's a super easy question, I don't know, but can I take this proof tree then and extract from it a BDD for the entire formula?
So, well, maybe the first thing I should say is that it's not necessarily a proof tree. It's a directed acyclic graph.
Right.
Okay. Now, what do you mean when you say you want to extract a BDD for the whole formula?
So,
well,
I guess, I mean, because when you say QBF, you mean, you assume that every single variable is quantified, right?
Yes.
So if I have a formula in which it's a partially quantified formula, and I leave some variables free, then I guess I could think of this as a Boolean function, right? So I'm just wondering, is there some kind of a, I mean, I've always been a bit fascinated with BDDs, so I'm just wondering if there's and there's a whole algebra of BDDs, right? So does do these operations in the proof tree somehow correspond to operations on BDDs? Maybe this question is not particularly well formed.
So I'm not very sure I understand in terms of a partially quantified formula and a BDD for that formula, because the BDD finally has to compute something. So I would need to understand what the semantics of what is it that we want the BDD to compute. So
I guess Pavel could be asking for like a BDD for the strategy for the universal player, right? Is that what
no, because that is what we are already doing.
No, I mean, I guess Anupam wrote in chat that obviously if we have a refutation, then the function is universally zero, right? But yeah, I mean, I guess.
So I think, so for instance, in the case of satisfiability, you could think of a function which outputs 0 or 1 when it is satisfiable and 0 when it is not satisfiable.
But maybe this is actually what I had in mind. I mean, since the universal player, since you have, let's say I have, you know, n universal variables and I have n BDDs, can I get a single BDD for the universal player out of this?
Okay, so if we want a single BDD, so this is something that was in fact used in this idea of combining it into a single function was used in fact to prove that equality is hard for QURES. Now, so what happens in equality, for instance, each variable, the BDD is trivial, you know, UI is equal to XI, just a one node BDD. But the moment you say I want one BDD which will query the x's in whichever order you want, and then at a sync node it should give me the values of all the u's. Okay, if I insist on one BDD which gives the values of all the u's, then such a BDD must have 2 raised to n nodes, because there are 2 raised to n different settings to the u's. Right? So just in terms of what is the range of the Herbrand function, the range is so huge that therefore your BDD will have to be large. This is where hardness comes for QURES, and I would expect that the same thing will happen even in merges. If you are going to build up a single BDD, this is one question. If the range is large, you cannot hope for a small BDD.
I see.
There is another question which is more subtle. Okay, so maybe the range is not large. maybe there are not too many, for instance, the parity formula, there are not too many universal variables. So the range of values that you need in a Herbrand function is just a constant. In the case of parity, it might be slightly larger. Maybe it is still not too large, it's polynomially large. There could still be a problem with combining these into different strategies into a single BDD, because semantically, the strategy for each variable is allowed to depend only on variables to its left. So now, for my last universal variable to be able to compute its value, the BDD must be allowed to query all the preceding variables. And then there are other universal variables along the way. And you have reached a node where you have queried things to its right, but somehow you should not be using that information. So to ensure that you don't use that information, semantically, you will have to put extra side conditions, which are the conditions that come out of our resolution, that are imposed by our resolution proof. So I'm not very sure, because we already impose these side conditions. If I combine this in some way, will it automatically be the case that they do not query variables that they should not? So this is something I should think through a little bit more.
Thank you very much. It's very clear. I think you've cleared up all my confusion. So, Anupam, please go ahead. You should be able to unmute yourself.
Hi, Meena. So a couple of questions. So one high-level question. So you showed the nice diagram at the end, and my understanding was that we had exponential lower bounds for all the systems you mentioned, all the resolution-based systems. Is that correct?
So these systems here in this box?
All of the systems in this diagram have exponential lower bounds. Is that correct?
Yes.
So, okay. And so they would be contained, are they all necessarily then contained in something like a Frege system for QBFs?
So these systems, your reductions, CP plus for all reduction up to here, this is definitely contained in the system, which is propositional Frege augmented with universal reduction. But I'm not sure whether IR is contained in Frege. I would guess it is, but I don't think that this has been formally written down.
Right.
So the expansion-based systems, how they compare with the Frege plus, because the Frege system that I'm thinking of is Frege plus universal reduction. I do not know of a expansion-based Frege system.
Oh no, I was thinking of something like, the pure logic Frege system. So something like if you take sequent calculus for second order propositional logic.
Okay.
This should be quite strong, right? We shouldn't have any bounds for this.
Yes, so I believe that these should all be contained there, but again, I do not think a proof of this has actually appeared anywhere. I do not, so I am not completely sure. I believe it should be the case, but I do not know for sure.
Yeah, I can also see how the ones in the box that should go through easily line by line, but for merge resolution that you presented, I suppose one also needs to encode the strategy information somehow, so it's a bit more subtle.
Yes, but so there is a system which is Frege plus universal reduction, which also in some sense encodes strategies, and that would certainly be simulated, I think, by the system that you are talking about. Yes. So if partial strategies can be represented there, I don't see why this merges will be a hindrance. It's really a question of how do you come. A line in this proof has a structure with multiple components. So how does the sequent calculus combine them all into a single object, which it can talk about?
Okay.
So
and then a low level but somewhat naive question, just to check. So the BDDs that represent strategies. These should be ordered, right? Induced by the ordering of the quantified variables?
No. So these are not OBDDs.
Okay.
So the BDDs that are constructed, it depends on the order in which you resolve the variables. So I think virtually all the formulas that I showed were like sigma 3 formulas. I never went beyond that. But let's say I have a sigma 5 formula. So my existential variables are in block 1, block 3, block 5. And I could have a resolution proof which gains from first doing a resolution on block 3 and then on block 1 on one path, and on another path first on block 1 and then on block 3. And both of these could play a role in the BDD. So there is no reason why block 1 and block 3 should be ordered in a particular way. All that I would insist on is that if I'm looking at a BDD for a universal variable in block 2, then it should not even touch block 3. But otherwise, there is no ordering constraint.
But at the end of the proof, you extract a winning strategy for one of the players in the evaluation game, right?
Yes. Yes. So that winning strategy that we extract, for each universal variable, it is looking at the variables before it, but it's not necessarily looking at them in any specific order. Because at the point when I want to decide U in the game, the values of all the preceding variables are known. Now, functionally, how I combine those known values, the order no longer plays a role, right?
Right.
And the BDD is just doing that. It's functionally combining the known values into a single right value for this variable U. Okay.
And then maybe one final thing from there. Is it known whether you can say something like, if you have any proof system that admits this sort of strategy extraction, that there's a lower bound for that? Is that like an interpolation method where you actually get a lower bound just from knowing you have strategy extraction?
So if you have, okay, let me try and think. So suppose I have a formal proof system which admits strategy extraction, by which I mean that from a proof of size S, I can extract a representation of a winning strategy of size polynomial in S.
Yeah.
That's what I mean, right? So now this would lead to lower bounds if I know that the Herbrand functions are hard in the chosen representation, the representation in which you extract the strategy.
Okay.
So for instance, for QRes and QUres, these are systems which do admit strategy extraction, and given any refutation in QUres, the strategy that is extracted is in the form of decision lists. So then my lower bounds are going to come from functions which are hard for decision lists. But if I'm going to extract strategies as circuits, then we don't have lower bounds. So that is what would happen when you are dealing with Frege plus universal reduction, or even with Frege plus universal reduction. You can extract strategies, but they are going to be formulas.
But don't we also have lower bounds on strategies themselves, like even in like an optimal representation? I mean, you can't have like.
Can I suggest that we maybe take a final question from the chat and move this to the discussion?
Yeah. Yes.
It's just that we're running a little bit over the usual time. Do you mind? So we have just one final question from Anantha in chat. Why do you use isomorphism? Can you not use a weaker notion of implication, where whenever M1 evaluates to false, then M2 evaluates to false, and in that case use M1?
No, so from what I understand, the question is we are performing a resolution on a variable which is to the right of the universal variable in question. So I'm performing a resolution, let's say on T. I have a universal variable U, and I have two strategies for U, M1 and M2. Now, whether I want to use M1 or M2 cannot depend on T at all, because T comes after U in the prefix. Suppose I just have an implication. M1 implies M2, and then I choose to use M1. Well, this may no longer be a winning strategy, because I may actually, okay, how do I go? So we are throwing away the situation where actually we needed the parts from M2, right? So whether M1 and M2 are true or false does not matter. What matter? I mean, to think of it as true or false is not the right. So M1 assigns a value 0 to U, M2 assigns a value 1 to U. So 0 is what helps in falsifying some clause, 1 is what helps in falsifying some other clause. So it's not that 0 is any better than 1, or so the implication in that sense makes no sense at all in this setting, according to me.
Okay, thank you. So as a final thing, I'm just going to ask everybody to unmute themselves, and let's give Meena a round of applause for this fantastic talk. And I will stop the recording.
Thank you very much.
Thank you.